A motor is primarily an inductive load. This is due to the presence of windings, which are coils of wire, in the motor's construction. When alternating current, or AC, flows through these windings, it creates a magnetic field. This magnetic field opposes changes in the current flowing through the circuit, which is the fundamental characteristic of inductance. Inductance is measured in Henrys. An inductor stores energy in a magnetic field when electric current flows through it. When the current changes, the magnetic field also changes, inducing a voltage that opposes the change in current. This opposition to current change is what characterizes an inductive load. In a purely resistive load, like a heating element, the voltage and current are in phase. This means they reach their maximum and minimum values at the same time. However, in an inductive load, the current lags behind the voltage. This lag is due to the back electromotive force, or back EMF, generated by the changing magnetic field in the inductor, which in this case is the motor windings. The amount of lag is quantified by the power factor. The power factor is the cosine of the angle between the voltage and current waveforms. For a purely resistive load, the power factor is 1.0, indicating that the voltage and current are perfectly in phase. For a purely inductive load, the power factor is 0.0, indicating that the current lags the voltage by 90 degrees. Motors typically have a power factor between 0.7 and 0.9, which means they are not purely inductive, but have a significant inductive component. The impedance of an AC circuit is the total opposition to the flow of current. It includes both resistance and reactance. Resistance is the opposition to current flow due to the material's properties, while reactance is the opposition to current flow due to inductance or capacitance. Inductive reactance is proportional to the frequency of the AC supply and the inductance of the coil. The higher the frequency or inductance, the greater the inductive reactance. Motors exhibit impedance because they have both resistance in their windings and inductive reactance due to their windings. The inductive reactance is typically much larger than the resistance, making the motor primarily an inductive load. When a motor starts, it draws a significantly higher current than when it is running at its rated speed. This is because the back EMF, which opposes the current flow, is initially zero when the motor is at standstill. As the motor speeds up, the back EMF increases, reducing the current draw. This high starting current can cause voltage dips in the electrical system and can potentially trip circuit breakers or blow fuses. To mitigate the effects of high starting current, various motor starting methods are employed, such as reduced voltage starters, which limit the initial voltage applied to the motor, thereby reducing the starting current. Another method is using a soft starter, which gradually increases the voltage applied to the motor, allowing it to smoothly accelerate to its rated speed. Variable frequency drives, or VFDs, are also used to control motor speed and starting current. VFD allow the motor to start at a low frequency and gradually increase the frequency to the desired operating speed, which reduces the starting current and provides precise speed control. The inductive nature of motors also affects the power factor of the electrical system. A low power factor can lead to increased current flow in the system, which can cause voltage drops and increased energy losses. To improve the power factor correction capacitors are often installed in parallel with inductive loads, such as motors. These capacitors provide reactive power that offsets the reactive power consumed by the inductive load, thereby improving the power factor. The size of the capacitor bank needed for power factor correction depends on the size and characteristics of the inductive load and the desired power factor. The power factor is typically corrected to a value close to 1.0 to minimize energy losses and improve system efficiency. When selecting motors for specific applications, it is important to consider their inductive characteristics and their impact on the electrical system. Motors with high power factors are generally more energy efficient and reduce the need for power factor correction. The motor's nameplate provides information about its voltage, current, power, and power factor. This information is essential for properly sizing the motor and ensuring that it is compatible with the electrical system. In summary, motors are primarily inductive loads due to the presence of windings that create a magnetic field when current flows through them. This inductance causes the current to lag behind the voltage, resulting in a power factor less than 1.0. The inductive nature of motors affects the electrical system in several ways, including increased current flow, voltage drops, and energy losses. Power factor correction capacitors can be used to improve the power factor and mitigate these effects. Understanding the inductive characteristics of motors is essential for electrical engineers and technicians to properly design and maintain electrical systems. So, for a theory test, the answer is inductive. Remember that inductive loads store energy in a magnetic field, and this affects the current and voltage relationship in the circuit. This understanding will help in answering similar questions related to AC circuits and motor characteristics.